to turn on. Okay, perfect. So here I will backtrack a little bit from the subleadings of theorems and go back to the leadings of theorems and see whether we have learned everything we had to learn from them. And actually, I will touch upon some of the things that Bob Wald discussed in his talk, although the angle of attack will be completely different. And so this is work well done in collaboration with Shranch, who is here somewhere. And so the idea that BMS symmetry and other asymptotic symmetries related to leadings of theorems are spontaneously broken is of course not new and has been discussed by numerous authors in the past, in particular by Andy and collaborators. But here I will try to revisit this idea, given what we've learned about, in particular, Carolean field theory recently. Yeah. And try to also adopt a perspective that is as quantum as possible, following essentially textbook QFT treatments of spontaneous symmetry breaking. So first, I will describe very briefly scattering states and the connection to Carolean conformal fields. And then I will go to BMS symmetries and their relation to soft graviton theorems, and see how they basically inform us about spontaneous symmetry breaking. And finally, once you've established spontaneous symmetry breaking, what you want to do is to run Goldstone theorem and learn something about the spectrum of your theory. So typically, in usual situations, you would predict the existence of a massless Goldstone modes. Here it will be a little bit different due to the different nature of the field theory we'll be considering. Okay, so I want to think about scattering theory. So in the Wigner paradigm, I want to scatter particles defined as unitary irreducible representations of the Poincaré group. So the Poincaré group will play a central role in this discussion. So here is the usual Poincaré algebra. And what I can do is simply change basis and go to a basis that will be more useful for us for both Carolean and celestial perspective. So basically, I'm splitting my mu index into 0, 3, and I, which will be 1 and 2. The Lorentz part of the algebra, which is SO1, 3, so I will write it in terms of 2D rotations, 2D translations, 2D special conformal transformations, and 2D dilation. That's the usual CFT description. And then for the translations, I will split into retarded time translation, into so-called Carolean special conformal transformation, and Carolean boost. So that's just a change of basis, but it will be useful. Okay, so now I will describe Wigner's construction explicitly in a way that will link to the usual way we parameterize massless particles in celestial CFT, celestial holography. So the way it works is that you pick a reference null momentum, K, and you ask, okay, what is the little group that leaves this momentum invariant? It's generated by this 2D rotation and 2D special conformal transformation. So you specify a representation of that in terms of helicity. And then what you do is you boost to an arbitrary frame by using the remaining boost generators, which here, I interpret as 2D translations and 2D dilation. And now I can, on this boosted particle, I can act with all my Poincaré generators and see what happens. And in particular, if I do it in this way, if I parameterize my boost in this way, what I rediscover is this particular momentum parametrization that we're used to in celestial holography. Okay, so that's a very brief review. Now, something that we don't usually consider in scattering theory is another type of unitary E-reps, which are zero momentum E-reps, so states that really have no momentum. These states, they basically reduce to unitary irreducible representations of the Lorentz group, the Lorentz subgroup. So that's a possibility we might want to consider. And we can construct them in a similar way. These are basically 2D conformal fields. Okay. The point is that if you ask for unitarity, you have three main choices. There's the so-called continuous principal series, complementary series, and exceptional discrete series. And I'm putting it here because I'm talking about E-reps of Poincaré. So at this point, you might wonder, okay, we're never using that in scattering theory, but you will see that it will actually play a role. Okay, so that's in principle the kind of spectrum I'm interested in. And now I go to Carolean conformal fields. So okay, there's a bit of history behind this subject, but I can also decide to construct them using group theory, just like Mack and Salam did back in '69 for usual conformal fields. And here the point is that I want to view Scry as a homogeneous space for the Poincaré group. So there will be an isotropy subgroup that leaves a point on Scry invariant. It will be generated by those generators, Jij, Bi, K, and D. And I will assign, I will just pick a representation of this isotropy subgroup. And then, like usual in field theory, I will translate my field using retarded time translation and 2D translations. When I do that, I land on these transformation rules for my fields. And what you can show is that if you have, there is a relation between those Carolean conformal fields and the usual massless particle states. This is what we would call an intertwining relation. So if this transforms like a Wigner E-rep, then this transforms like a Carolean conformal field. Yes?
Just a technical question that you are so you are here assuming that the Carolean boost operator acts trivially on your field when you are at the origin, right? Because it commutes with it. So in which sense is it restrictive on, or what hypothesis physical hypothesis behind this you can invoke to justify this?
Okay, so yeah, that's a restrictive choice. Mm-hmm. You might want to do more than that. Let me think. So, in fact, in a recent paper with Jakob, we do propose new types of representations where boost acts non-trivially, and I think it's, now I don't remember for which type of situation it's important, but
for magnetic Carroll fields, for instance. Because there you have undecomposable, irreducible representations.
Yes, basically. Indeed. So so that's true. If you do that, you will end up with something that is reducible but indecomposable, and that will. Okay, so that's also interesting. Here, I just wanted to make the connection with the usual one-particle states.
Okay.
Okay, so you have this relation. So now that you have this relation, that basically tells you just at kinematic level, that if you have a scattering amplitude between massless states, if you apply this transformation, you will have something that has the kinematics of a Carolean conformal correlator. And so that we will use. Now the usefulness of doing that is because now BMS symmetries will act in a local way, and then I will be able to tie back to the usual description of spontaneous symmetry breaking in QFT. So I'm going to consider BMS4. So we still have the Lorentz group, but we have now, instead of like a four-dimensional abelian group, I have the super translation group, which is defined in terms of weight minus 1 functions under the Lorentz group. And if I consider now the way those one particle fields, Carolean fields, transform, they simply transform well, by a retarded time derivative. So that's the action on these one particle fields. From that, I can naturally write down a word identity. So now instead of one field, I consider the action on a product of fields. And I sandwich that inside the vacuum, what I would call the vacuum. So now if the vacuum was BMS invariant, this first line would be 0. But we have to be open to the possibility that it may not be 0. And in fact, this is a way to basically diagnose whether the vacuum spontaneously break or not, the symmetry. This would be called order parameter, if you like. So we're gonna now go to the next step and see how the Weinberg-Soft theorem basically tells you that the vacuum does not, breaks BMS symmetry.
But, I mean, of course, this language was already refined in the 1960s when it was realized that the equation, the non-vanishing of the right-hand side says that Q is not a self-adjoint operator acting on the Hilbert space, right? That you have an automorphism of the algebra that cannot be promoted to a unitary transformation within a Hilbert space. Right? And you don't need that to derive the Goldstone theorem and all the consequences.
Okay.
Symmetry breaking.
Yeah, I'd be interested to look into that. Maybe here I will propose something a bit different in language than that. So let's wait perhaps a moment. So I will just follow my nose and see where it takes me. So I'm taking now the Weinberg-Soft theorem, soft graviton theorem, which is written here. And if I use this parametrization of null momenta, so here everything is massless for simplicity. If I take the parametrization of the momenta I had before, this soft factor takes this explicit form in terms of points on the celestial sphere. And what I can do, as I was saying, is I can go to the Carolean basis by applying the kind of Fourier transform we had on one of the previous slides. And I will apply this Fourier transform only on the hard legs. So this is why I go from this P1 to this O1x. But the insertion of the soft graviton, I leave it as it is. And then on this side, you see, well, this omega turns into a du derivative. And at this point, well, you can recognize that this right-hand side is basically the right-hand side in the BMS word identity I was showing previously, provided you identify this as the super translation parameter, which will depend on the direction of the soft graviton. So it's a particular choice of function. And on the other side of the equation, you will naturally try to identify the soft graviton insertion as the action of your supertranslation charge on the vacuum. Although this might be just a little bit formal and not mathematically well-defined. And we'll see later how we can improve on that situation. So yes, so basically here, just comparing the soft graviton theorem with BMS world identity, you're kind of forced to conclude that BMS is spontaneously broken just because this right-hand side is non-zero. Okay. So now I will, go to a Crowleyan version of the Goldstone theorem. So you've established spontaneous symmetry breaking, and you want to know what it means in terms of spectrum of particles. So to do that, what we need is to write an explicit expression for the super translation generator in terms of a current. So here, I will write my super translation charge as an integral over cutoff scribe at fixed u of the Bondi mass aspect. And here, I'm using a specific, in our work, we're using a specific version of covariant Bondi mass aspect, which is such that, okay, when you push this u to minus infinity, this is the true canonical generator of BMS symmetries, also including covariance under superrotation. But in fact, for the purpose here, it's not too important what kind of, what choice you make for this Bondi mass aspect. But the important part is that as you go to like the path of future null infinity, so towards spatial infinity, this is a proper canonical generator. And you can see that there is a non-conservation equation for this Bondi mass aspect, but this non-conservation turns into conservation as you go to spatial infinity, because as you go to spatial infinity, this thing has to be the canonical generator. Okay, so when we discuss spontaneous symmetry breaking, we need an order parameter that is non-zero. And in this case, the order parameter was this quantity where O was a product of one particle fields. And we've established it's non-zero. So now what we do is that we're inserting a resolution of the Hilbert space in between Qt and this product of states. And because it has to be non-zero, there must at least exist one state that we will call the Goldstone state, such that this matrix element between the vacuum and the Goldstone of this canonical generator is non-zero. Or equivalently, that the Bondi mass aspect sandwiched between 0 and one of these states is non-zero. Okay, but at the same time, there is a conservation equation. And in fact, so here, because I want this to be canonical generator, I really have to go to spatial infinity. So this is why I'm doing that now. So as I go to spatial infinity, this Bondi mass aspect is conserved. This Bondi mass aspect I can rewrite in terms of the Bondi mass aspect as 0, but like using the retarded time translation operator. Now this guy acting on the vacuum just gives 1. And here, the only U dependence is here now. And I can use this to act on the Goldstone state. Now, if I were to consider a usual massless particle state, acting with H on this massless particle state would give me omega. And so this will not satisfy this relation. So I have to actually consider a state which has strictly zero momentum. And this is why, I discussed these zero momentum representations at the beginning. It's because I'm led into concluding that the Goldstone must be one of these. So the Goldstone will be of that form. It will be a 2D conformal field on the celestial sphere. And the choice of, so you remember you had various options for the scaling dimension such that it's unitary. And here I'm picking delta equal -1 just because that comes from the super translation group. So remember the super translation group was described in terms of weight -1 functions on the sphere. So it's natural to consider the Goldstone to be a dynamical version of this thing. Yes. And this happens to be in the so-called exceptional discrete series of these representations. So let's see what this tells us. And I think this is the perhaps most interesting part because it touches back upon discussions we had this morning with Bob Wold regarding the nature of the Hilbert space. So here, the thing is that unitary representations, they come equipped automatically with a Hilbert space structure. Because when you say unitarity, it's unitarity with respect to some inner product. And there is a unique inner product given, one of these representations. For the exceptional discrete series, it happens to be of this form, which is very peculiar, because in addition to the usual power law, you also have a logarithm. And that's very interesting because this was argued already some time ago by Andy and collaborator to be exactly what you need in order to account for infrared divergences.
Is Curlian divergent here? Is 1/epsilon? Or?
So here, group theory doesn't tell you what this is.
Because that's important in the references you wrote below, right? 2000.
Yeah, group theory, I know that there, you can shuffle around where you want to put the 1/epsilon. Here, the group theory doesn't tell you what this normalization is. So here, I'm just using group theory, and group theory, leaves that up to you, depending whether you want to normalize. Naturally, there will not be a 1/epsilon because you will try to impose some sort of unit norm on your basis states. So naturally, this would be 1. But
so in this sense, it's a bit different from the
well, yeah, I'm not discussing the numerics. I'm just saying that while this has been, I think people have been confused as to how you can have such a two-point function in a CFT. But actually, when you go to these discrete series representations, it's automatic. You have, it's provided to you by the inner product on the Hilbert space. So I think this suggests, and a note, so these exceptional discrete series are exceptional. This is why there are exceptional subtleties. When you consider actual normalizable states of this form, so these are basis states, but when you smear them with some wave function living on some appropriate functional space, the scale dependence actually is irrelevant. Now, I think this suggests is that, well, because remember, the superrotation, the supertranslation charge acting on the vacuum was, you wanted to identify it as a soft gravitonic insertion, so related to the Goldstone mode. Here, what this group theory is suggesting is that you should remove the soft graviton from the Hilbert space, the Hilbert space of graviton, and that we know, I mean, Bob told us this morning that a Weinberg pole is incompatible with the norm on the graviton-Hilbert space, so that you remove from the graviton-Hilbert space, and instead you give it this Hilbert space, which is associated to this particular exceptional series representation. Well, that's basically what I wanted to say.
I have two questions. The first is, can you go back to where you said delta equals -1 and explain why it's -1? Because supertranslation is naturally related with delta equals to 1.
Yes, so, okay, I could have, yeah, delta equals -1 is basically, okay, as I was saying, because typically Goldstone modes are dynamical versions of symmetry parameters. Here, you know, an element of this group is a weight -1 field. I mean, weight -1 function, so it's natural to think that this is the weight you have to give to your Goldstone particle. Now, potentially there is a more direct way to show it, but okay, at this point, I don't really.
Minus a half. It's a half. That's the
Yeah.
delta equal -1. Is the other guy.
Yeah. No, go ahead. Okay. So, any hope of doing this also for super rotations?
I haven't thought too much about, well, of course it's a natural question. Yeah, I haven't thought of the symmetry breaking pattern of you know, super rotations down to Lorentz, but you could think of doing that. Here it's especially simple because the group that you're breaking is abelian, so it's particularly simple.
Yeah, first I think I gave myself the answer to my first question, which is that if you take two... The mic is on. No, it's on, it's just bad. If you take two derivatives, the primary descendant, then you land on delta equals to 1, which is the dimension of the
No, yeah. So I mean,
so that's the
of course we knew. I mean, this is not something new. This delta equal -1 for the Goldstone mode. It's something that.
It's the top of the conformal multiplier.
Yeah. So I mean, that's already. I mean, in many papers you kind of can find that. I think what has not been realized is that if you really insist on these belonging to a unitary reducible representation, then it buys you something, which is this Hilbert space structure.
And then the actual question is, so you want to throw out the soft graviton now, but also the memory, or because the two are symplectically paired, so if you throw out one, maybe you should throw out the other two? Or?
Yeah, I mean, I don't have really a comment on that because here, as you can see, I have tried to free myself as much as possible of like of prior descriptions. Here, I'm really only assuming unitarity, the Weinberg soft graviton theorem, and that's it. And so I'm led into this description, but I don't have here the memory mode. I don't necessarily see it at this point.
Yeah, here. Question. Can you hear me? Yeah.
Yes.
Are these exceptional series related to conformal anomalies?
how they're related. So I think one thing I should really emphasize is that, well, and that should be obvious from this classification here, that this is not standard conformal field theory. Standard conformal field theory is unitarity with respect to SO2,2, or reflection positivity with respect to SO1,3. But here I'm talking actual unitarity with respect to SO1,3.
Yeah, just a comment on Andrea's question. Maybe I think this construction is very similar to what we did with Laurent and Anna on the discrete basis, and the delta minus 1 comes from the fact that the Goldstone is the d square of the. I mean.
Yeah, but that's what we had.
No, no, I mean.
Yeah, yeah. Yeah, okay. Yeah, and yeah, the 2-point function also looks very similar to the one that we have for this discrete series. And the memories indeed are related to the Goldstone. There is like somehow a relation between the Goldstone and the memory. So you should probably have a formulation of this Hilbert space in terms of memories or with discrete labels as well.
Yeah. I mean, I think, many of the things I'm saying here have appeared in some form in the literature. But here I've tried to emphasize, and the approach taken here is to run the Goldstone argument in the usual way, which is you're kind of agnostic about the theory you're dealing with. You know there is a symmetry. You have an observable called order parameter, which tells you that the symmetry is broken, and then you run Goldstone theorem, and it tells you what kind of spectrum you have. But okay, that doesn't mean that, of course, this cannot be, this connects to a lot of
I'm just saying makes sense, that's what I'm saying.
Okay.
Just a quick comment is that there is a well-defined Hilbert space which captures generic BMS representations and which has the soft, the hard, and also the generic one, which is...
Right, so now you're talking about BMS representations. No, that's also an interesting an interesting comment. Yeah, here I'm formulating everything in the usual Poincaré scattering theory.
And you can see how they branch on the...
Okay.
I'll ask a quick question.
Yes.
Quick answer.
Yes, so first a comment to follow up on Simon's question. Actually, for super rotations, you also have a Goldstone mode, which is this Liouville field we found with Romain and Geoffrey. And then this field also has a correlator, which is a log. And this is instrumental in showing that actually the celestial CFT is in fact a log CFT which evades the C equals 0 catastrophe. And what is even more instrumental is that the curly N you have is also, as Laura mentioned, inversely proportional to the cusp anomalous dimension of the amplitude. So do you think there is a fundamental understanding of why this factor is always divergent? Because I know that from group theory, you just have the log, that's it.
Okay,
but, yes.
So there's many aspects to your question. Yeah, so, okay. One aspect is that you mentioned log CFT. Log CFT has a particular structure, which is that you have at least a pair of fields that sit into an indecomposable representation of the dilation operator. Mm-hmm. Here, it's not necessary because, and by the way, the guy in the log CFT doublet, which has a logarithmic 2-point function, does not transform into itself. While here, the conformal fields sitting in this exceptional discrete series, they don't have this anomalous transformation, so they live perfectly well with themselves, although they have this log 2-point function. Another aspect is that you mentioned the Liouville field. So, of course, that's an interesting point.
We can continue
Yeah.
because it's...
We will discuss together.
Short answer.
No, the short answer is that probably you're right, but that it would be interesting to run this kind of analysis that is, purely QFT and kind of agnostic about most of the details.
Exactly.
Of the
That's what I wanted you to say. So, okay, thank you.